Hey, this is Ken Rosever, and here's another video. Something I think I'm beginning to see as I'm teaching stats is that sometimes we do calculations and we follow examples in the book without reading through the chapter. And without reading through the chapter, we don't really come to understand what it is that we're actually doing. So my goal in this video is to show you guys what is an interval estimate and why do we care. This is not going to be a video about how do we calculate them. I have other videos for that. This is just a background video on what is this interval estimate thing and why is it important? How is it useful? Okay? So let's begin. Anytime we do an experiment and we take a sample out of a population, dependent on its size and what is known as sampling error, the sample may paint a quite accurate, approximate, or somewhat loose picture of the population from which it came. See, a sample represents the population, but is not equal to the population. So anytime we take a sample, there's always some uncertainty to it. However, rather than just say that, well, sampling doesn't work and we can't use it to tell us anything about the population because you never know, you might get some bad samples and they'll tell you something that isn't true. Rather than say that, statistics allows us to calculate estimates of these parameters, these characteristics of the population. It allows us to qualify them and calculate an interval about them so that we're not just saying, here is what the sample says, and therefore, because the sample says this, it must be true about the population, because we know that's not true. Rather, we say, here's what the sample says, and therefore, it must also be true that the population is in the ballpark of that number. All right, let me be more explicit and use an example to be a little more clear here. Okay, let's say that this is a distribution of dog weights in the United States. Dog weights in the United States. Now, it's probably actually the case that a distribution of dog weights would be positively skewed, which means the hump would be on the left. But we won't worry about that. We'll just say this is it. Now, if I begin to sample out of this distribution, and I sample randomly, because that's always a key. I want to sample randomly. If I'm doing dog weights in the US, I want to get dog weights from all over the place, many different zip codes and whatnot. I want to use some kind of random number generation scheme to point out and pick certain dogs in certain areas and certain zip codes owned by, whatever. So let's say I do this, and my sample, randomly selected, comes in like this. So I end up sampling, you can see I ended up sampling more on the left than I did on the right. So what's that going to do? It's going to give me a sample mean that is less than my actual mean of the population. So and that can happen because this is all random. So could this happen? Absolutely. It could also happen that when I sample, that I could get more samples on the right than on the left, or I could get equal numbers of samples on the right and the left, but let me do this. Let's say the ones I get on the right are here and the ones I get on the left are more out here. Now these will have a greater effect on the sample mean than these guys. Okay, these guys will pull the sample mean to the right of the actual mean. So in this case, mu is less than the sample mean, and that can happen. But it should always be the case that mu is somewhere around there. Okay, it's in some neighborhood of the sample mean when I do this. So, and hopefully when you do a random sample, you'll actually get a more even distribution where you get more, obviously you would get more samples from in the middle than you get on the extremes, okay? And when you do, your sample mean should end up approximating your actual mean for the population. But even, accounting for sample error, there should be a ballpark or a buffer that if I have the sample mean, I can go so far to the right and so far to the left, and somewhere in that interval, the mean will be in there. Let me keep reading what I wrote here. Okay, so statistics allows us to calculate an estimate of these parameters based on sample statistics and qualify those estimates by calculating an interval about the point estimate. I just said the point estimate. What's the point estimate? The point estimate is the best estimate we have at the time of the mean, the actual mean, or if we're doing standard deviation, the standard deviation. Now I'm doing mean because it's easier to visualize. So the sample mean is the point estimate. It's the best guess we have of the mean. So if I had to guess one number, you know how you look sometimes at a jar full of jelly beans and they tell you guess a number and the person who's closest wins? Well, if I had to guess a number, I would guess X bar. That would be my guess. It's my point estimate. It's my best guess. But in statistics, we don't want to leave it at that because it's very unlikely, unless our sample's huge and unless we're rounding off the values, that our X bar will match our mean exactly. So we're going to go beyond the point estimate and we're going to develop an interval estimate. See, not just a point. Here's a point estimate. Okay, on a number line, it says, here's some values, and let's say that my point estimate comes out 38 pounds. Okay, that's my X bar. Well, that would be my point estimate of mu. But I'm not going to limit it to that. I'm going to do an interval estimate. And an interval estimate says that it's probably not exactly there, but it's in the ballpark. So I'm going to create, let's say I create a buffer of 4 pounds in each direction. So an example of an interval estimate would be 34 pounds up to 42 pounds. So my estimate for mu would be, mu is between 34 and 42. Now the size of the interval is determined by a number of factors. It's determined by the sample size, the population standard deviation if it's known, or if it's not, the sample standard deviation, along with another factor which is related to how certain you want to be about the interval. So the interval acts as a buffer around your estimate. Since we suspect that the point estimate is hopefully close, we add and subtract a value in both directions. We extend our estimate outward in both directions. So we're saying, it's probably not right at 38, but it's in the ballpark. Now, I said 4 in each direction, but normally, how far we go in each direction is not something we just randomly guess and select. We don't just pull it out of the air. It's based on those factors I just mentioned. So let's go over those. There's 3 factors that determine the width of an interval. Let's go there.